Hello everyone. In today's video, we'll be discussing on RC oscillators. Here is the content for today's video. Firstly, we'll be discussing about the introduction, followed by what is RC oscillator, working principles of RC oscillator, types of RC oscillator, RC phase shift oscillator, working of RC phase shift oscillator, Wien bridge oscillator, working of Wien bridge oscillator, applications of RC oscillator, advantages of RC oscillators, limitations, and finally the conclusion. Introduction. Explore the diverse types of RC oscillator and their functionalities in this presentation. Understand the fundamental working principles that govern the operation of RC oscillators. Discover real-world applications where RC oscillators play a crucial role in electronic systems. Summarize key insights and findings leading to a conclusive understanding of RC oscillators. What is the RC oscillator? An RC oscillator utilizes resistors and capacitors in a circuit to generate oscillations. This type of oscillator is frequently employed in electronic devices for the purpose of generating clock signals. Additionally, RC oscillators serve as crucial components in creating precise timing references for various applications. Working principle of RC oscillator. The working principle of an RC oscillator hinges on the utilization of the feedback to maintain oscillations. The frequency of oscillations in an RC oscillator is dictated by the characteristics of the resistor-capacitor network. The amplifier in the circuit plays a critical role by supplying the requisite gain for sustaining oscillations. Types of RC oscillators. In this video, we'll be discussing about two types of oscillators, that is two types of RC oscillators, the Wien bridge oscillators and phase shift oscillators. Each type of RC oscillator possesses distinct characteristics that contribute to its unique functionality. These oscillators find applications in diverse electronic systems due to their specific attributes and performance. RC phase shift oscillator. The RC phase shift oscillator generates oscillations by utilizing a phase shifting network. This oscillator is widely applied in the field of audio equipment due to its effectiveness. In communication systems, the RC phase shift oscillator is a common choice, showcasing its versatility in various electronic applications. Working of RC phase shift oscillator. Here is the circuit diagram for the RC phase shift oscillator. The core of the RC phase shift oscillator lies in its feedback network comprised of three identical RC stages connected consecutively. Each RC stage within the feedback network contributes a 60-degree phase shift to the signal, collectively establishing a total phase shift of 180 degrees across the three stages. The inverting amplifier stage in the circuit introduces the fourth and final 180-degree phase shift, completing a full of 360-degree phase shift for sustained oscillations. Positive feedback characterizes the RC phase shift oscillator, ensuring that the output remains in phase with the input, completing the full 360-degree phase shift and sustaining oscillations. The sustained oscillations are a result of the positive feedback mechanism in the circuit. The frequency of oscillation is determined by both the time constant of the RC stages and the gain of the amplifier. The frequency f can be calculated using the formula f is equal to 1 by 2 pi RC root 6, where R is the resistance and C is the capacitance of each RC stage. Wien bridge oscillator. The Wien bridge oscillator is a specific type of RC oscillator which employs a bridge network to generate sine wave oscillations. Its unique design and functionality makes the Wien bridge oscillator well suited for applications in the audio frequency range. This oscillator stands out for its capability to produce precise sine wave outputs, contributing to its widespread usage in audio applications. Working of the Wien bridge oscillator. Here is the circuit diagram for the Wien bridge oscillator. The critical component of the Wien bridge oscillator is its feedback network, which comprises of two resistors R1 and R2 and two capacitors C1 and C2 arranged in a bridge configuration. Designed for a specific frequency, the bridge network introduces a 180-degree phase shift as part of the feedback mechanism. The amplifier stage of the Wien bridge oscillator incorporates an operational amplifier with the bridge network connected to its inverting input. To complete the 180-degree phase shift, the op-amp is configured in such a way that its non-inverting input is grounded. The frequency of the oscillation in the Wien bridge oscillator is determined by the values of resistors R1 and R2 and capacitors C1 and C2 within the bridge network. It is expressed by the formula F is equal to 1 by 2 pi RCF. The frequency F is dependent on the resistance R and capacitance C in the network. The frequency F can also be determined as F is equal to 1 by 2 pi RC1. The positive feedback from the bridge network ensures the sustained oscillations in the Wien bridge oscillator. The combination of the phase shift introduced by the bridge network and the 180-degree phase shift from the op-amp fulfills the Barkhausen criteria, allowing the circuit to meet the conditions for the stable oscillation. Applications of RC oscillators. RC oscillators are extensively applied in electronic devices, serving crucial roles in clock generators, frequency synthesizers, and signal generators. The versatility makes RC oscillators essential components, ensuring stable timing references in a variety of electronic applications. From precision timekeeping in clock generators to generating specific frequencies in synthesizers, RC oscillators contribute to the reliability of diverse electronic systems. Advantages of RC oscillators. RC oscillators present several advantages including simplicity, low cost, and versatility in oscillation generation. These qualities position RC oscillators as favorable choices, making them suitable for a broad spectrum of applications. The combination of simplicity and cost effectiveness enhances the appeal of RC oscillators, allowing them to find utility in diverse electronic systems. Limitations. Despite the advantages of RC oscillators, challenges like frequency stability and temperature drift may arise. To address these limitations, careful design and meticulous component selection play a crucial role in enhancing the performance of RC oscillators. Mitigating challenges such as frequency stability and temperature drift requires a strategic approach to design and selection of components in the construction of RC oscillators. Conclusion. In conclusion, this presentation has delivered a thorough examination of RC oscillators encompassing types, working principles, applications, advantages, and limitations. The significance of RC oscillators in electronic devices has been underscored throughout the presentation, emphasizing their importance in various applications by exploring their types, operational principles, and addressing both advantages and limitations. This presentation aims to provide a holistic understanding of the role of RC oscillators played in the realm of electronic systems. Thank you.